Hello, everyone. Welcome to the Math Magician's Den. We are going to talk about continuity. What does it mean for a function to be continuous at a specific point, at a value c? Most people will tell me for something to be continuous, for a function to be continuous, you need to be able to draw that function without picking up your pen. Well, in calculus, we go into a little bit more depth than that. Number one, if I have a point right here, and let's say this is x equals c, and this is your function f of x, there are three things that need to happen. Number one, and I think this one might be the obvious one, the point right there at c has to exist. F of c has to be defined. There has to be a point there. Okay? Secondly, what's the second thing that has to happen? I'm trying to use some lighter colors here. The limit from the left over here should approach the same thing as the limit from the right. The limit has to exist at c. And then these two, once they're satisfied, they have to give the same value. The limit is x approaches c of f of x has to equal f of c for the function to be continuous. This is the definition of continuity when we're talking about calculus. Now, for a function to be continuous on an open interval, it just has to be continuous at every single point on that open interval. Okay, and it's the same thing when you go from negative infinity to infinity. If that's the case, if it's continuous from negative infinity to infinity, we say the function is continuous everywhere. Now let's take a look at these graphs down here. Number one, this first graph, I think is pretty obvious. If we test part one, can all of you tell in this picture that f of c is not defined? Why is f of c not defined? There's a hole in the graph. So this one literally fails the first test for continuity. So we can stop there and we can say f of x is not continuous at x equals c. Good enough. That's all I have to do on that first problem. Now, on the second problem, let's test number one. And let's say these are values 1, 2, 3, 4, 5 on the y-axis for all of these graphs. Right here, that dot, f of c, is defined. And here's what I'd like to do too. What is f of c? Well, it looks to me in this picture like it actually equals 4. The y value is 4. So the first one is satisfied. There is a point on the graph at c. But the second thing that has to happen, the limit as x approaches c of f of x has to be a number. It has to exist. Well, it looks to me here like the limit from the left over here is approaching 3. The limit from the right over here is approaching 4. So this limit does not exist. In fact, I'll give you a reason. The left-hand limit, which is 3, does not equal the right-hand limit, which is 4. So guess what? This second part fails. F of x is not continuous at x equals c. And again, I don't need to check the third condition because number 2 failed. Now let's do one more here. Okay. Let's check number 1. Right here on the graph, there is a point at c. F of c is defined on that third graph. In fact, it looks to me like it equals 2 if we're jumping by ones again. So the second part of my definition for continuity, the limit as x approaches c of f of x. It has to exist. Well, it exists. Why? If you look at the graph, here it approaches from the left the same thing that it approaches from the right. But it looks to me like both sides approach 3. The limit is 3. So it passes the first test, passes the second test or condition. Now the third condition, the limit as x approaches c of f of x, well, that has to equal f of c. But the limit is 3. And the f of c is 2. It looks to me here like they're not equal. So it fails part 3. So again, we can say that f of x is not continuous at x equals c. Now, once we decide that there are discontinuities, we have to decide what kind of discontinuities they are. And what is a discontinuity? If you have a function f of x on some open interval that contains that value of c, in other words, just figure an open interval somewhere around c. F of x is not continuous at c, you have a discontinuity at c. And there are two types of discontinuities that we actually talk about. The two types of discontinuities we actually talk about are a removable discontinuity, which is simply a missing point or a hole in the graph. And here's something I'm going to add to that definition. The limit as x approaches c of f of x, that limit, it exists. So if you see a discontinuity in the graph, and you can honestly say that the limit exists at that point, at that spot, it's a removable discontinuity. It's a hole or a missing point. We'll show some examples of that in this video. An asymptote, or a jump in the graph from one y value to another, that's called a non-removable discontinuity. And in this case, the limit as x approaches c of f of x, this time it would not exist. Asymptotes, two things can happen. It can go to infinity, or it can go to negative infinity on each side. So those cases, with asymptotes, the limit would be unbounded. With a jump from one y value to another, the left-hand limit would not equal the right-hand limit. So that's a reason for having a limit that does not exist. And these are what we're talking about with, obviously, two-sided limits. So I'm going to do 4 examples for you here. And each of these 4 examples, what I'm going to have is I'm going to have a graph that involves a discontinuity at x equals 5. Now, this first one is a piecewise function. It equals -2 right here until I get to 5. And at 5, I cannot include the 5. But then when I get to 5, the value of the function is 3, and it equals 3 after that all the way across the graph. So this piecewise function involves 2 different horizontal lines. One, y equals -2 until I get to 5. And then from 5 to infinity, I have to graph y equals 3. I think all of you can tell there is a discontinuity at 5. It's a jump. Okay. Now, some classes will allow you to say jump. For me, I think you can see that a jump from one y value to the next, the limit doesn't exist. So what we're talking about here is a non-removable discontinuity. And I'm just going to put DSC for discontinuity at x equals 5. I think it's pretty obvious. Now, you may have to give the reasons on a test or on an AP exam as to why it's not continuous there. Well, we're going to check our 3 conditions. Part 1. Does f of 5 exist? Is it defined? Yes. F of 5 is defined. Can you all see what f of 5 is? F of 5 is 3. Part 1 is satisfied. Now, part 2, we also have to have the limit as x approaches 5 of f of x here. It has to exist. Well, guess what? It does not exist here because the left-hand limit, which is -2, does not equal the right-hand limit, which is 3. So part 2, okay, does not happen. This has a discontinuity at 5. It is a removable discontinuity at 5. Now, let's take a look at 3 more graphs. This particular graph, if you want to pause the video and you want to graph it on your calculators, what you're going to see is you're going to see a line. In fact, this graph right here, if you factor it, it comes out to be x minus 5 times x minus 2 over x minus 5, and the x minus 5's cancel. This graph actually looks like x minus 2, but when you get to 5, and you guys can try it on your graphs there, it doesn't have a value. In fact, it has a hole. And that's what some people will say about this graph. This graph has a discontinuity that's a hole, which is fine. But what kind of discontinuity is that? This is a removable discontinuity. at x equals 5. I remove the point from the graph. Now we're going to go through the steps again. Step 1. Is f of 5 defined? Well, it's not. There is no point at x equals 5. We can stop. I have a discontinuity at 5 because it fails the first condition. I don't even need to check the next two. But the one thing I do notice here, if I were to write down step 2, it would be satisfied because the limit as x approaches 5 of f of x. Sorry, I drew a very crappy 5 there. It looks like on both sides it approaches 3. So the limit does exist. That's why this is a removable discontinuity. How'd I get 3? Right here. This graph looks like x minus 2. What's 5 minus 2? It's 3. That's my limit. Now, we're going to do a few more things here. This next graph is a piecewise function. It literally involves the graph from the previous one. So at 5, 3, there's going to be a hole. This still looks like the line that I drew the last time, but there's an extra point on this graph at 5, 5. I just added a coordinate. Now, this has a hole in the graph again, and some people will say, yeah, because of the hole, this has a discontinuity. But what kind of discontinuity is this? I took a point, I removed it from the graph, and I put it somewhere else. This is a removable discontinuity at x equals 5. Now, again, I'm going to show you why it's a removable discontinuity in just the next few minutes here. Step 1, does f of 5 exist? Is it defined? It is defined. In fact, f of 5 equals 5. It's that coordinate. So part 1, satisfied. Part 2, and this is why it's a removable discontinuity. The limit as x approaches 5 of f of x, it exists. In fact, it equals 3, just like the previous problem, because it's just that line repeated again. Where we run into problems is part 3. This one is not satisfied, and this is why I've got a discontinuity. The limit as x approaches 5 of f of x, which equals 3, that does not equal 5, which is f of 5. So the last condition is not satisfied. There is a discontinuity here on this graph. And let's do one more here. I hope all of this information is making sense to all of you. On this next graph, if I were to graph it, there is nothing at 5. If I start on that first graph, and I start at 3 and I go up by 1s, when I get to 8, there is an open circle. Or when I get to 5, 8, there's an open circle. The next graph actually starts at that same spot. And if you took the time to graph this, you would see 2 lines. They actually meet at this open circle at the coordinate 5, 8. I think it's pretty obvious. Again, this is a hole. This is a removable discontinuity. I know I haven't shown an asymptote here. I'm going to try and show more of those in future videos. For now, this is a hole, and here's why it is a hole. Part 1, it is not satisfied. F of 5 is not defined. Now, we could stop there, and we could say, hey, this is not continuous at 5. If I went on to step 2, it is satisfied. The limit as x approaches 5 of f of x here, well, it equals 8. That's why this is a removable discontinuity. Try to remember with discontinuities, if the limit exists on that graph at that discontinuity, it is a removable discontinuity. If the limit does not exist at that value of c, it is a non-removable discontinuity. I hope you enjoyed the video. If you did, hit the like button. Also, if you're enjoying the videos I've been posting and it's helping you, maybe subscribe to my channel. I will be posting more videos as time goes by.